Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 17th lecture on numerical inverse kinematics. So let's get started with a video. And in this video, I've got a spider-like robot. And the really cool thing about this robot is that it does not know its own kinematics. And it's going to try to figure out its kinematics over time through trial and error. Now, in simulation, the robot proposes different versions of its kinematics, maybe different places its legs could be and different ways those legs could be connected. And then in reality, my robot's going to try moving and collecting data. And we're going to try to see how well that data matches with what the robot thought its kinematics were in simulation. Over time, the robot is able to build a pretty accurate kinematics model. And so the next thing the robot does is it uses this kinematics model in order to try to figure out how to walk. So here you can see a gait that this simulated robot has come up with. So I've got my kinematics, I've tried to use them in simulation, and now I'm going to apply what I've learned in reality. And so this robot, which originally did not know its own kinematics, is pretty rapidly able to figure out those kinematics and then walk across the table. I think it's an interesting video, and it connects to today's lecture, which is again about kinematics. Specifically today, I want to talk about inverse kinematics, and I want to show you an algorithm that we can use to find the inverse kinematics of a serial robot arm. I'll start off with that, and then I'll also show you some pitfalls of this algorithm and maybe how we can deal with these failure cases. All right, so let's get started. Before I can show you the algorithm, I have to introduce one final component, and that's going to be a way to convert from a transformation matrix into a vector. So you guys remember that a transformation matrix T contains a rotation matrix and a position vector. This rotation matrix will be 3 by 3, the position vector will be 3 by 1, and overall my transformation matrix is a 4 by 4 matrix. But for my inverse kinematics algorithm, I'm going to need to convert this 4 by 4 matrix into a corresponding 6 by 1 vector. I'm going to do that using this log of t operator. So the log of t is going to take me from my transformation matrix, t, into this 6 by 1 vector you see right here. The bottom three elements are probably the easiest to understand. That's just my position vector. So I just take my position vector and write it here, all good. The part that's a little bit more confusing is how I go from a rotation matrix into this vector omega. And the idea is I'm going to take my rotation matrix, I'm going to extract the angular velocity that corresponds to that rotation matrix, and that's going to be the omega that you see right here. I'll show you some code for how we do this. Now this is a function that I wrote in MATLAB in order to perform this log of t operator. I'm going to take in my transformation matrix, again, that 4 by 4 transformation matrix, and I'm going to output this 6 by 1 vector x. So my first line, I'm just declaring, yep, I want to output a 6 by 1 vector. In the next line, I take my transformation matrix and I extract the corresponding elements for the rotation matrix. So I've got my rotation matrix, I'm going to call that capital R. Next, if you remember from a previous lecture in this course, we know that there is a way to go from angular velocity to rotation matrices, and that uses the matrix exponential. So I've got my bracket 3 of my omega, so that my angular velocity is omega. I take the bracket 3 operator of that angular velocity, I can take my matrix exponential, and I can build my rotation matrix. And again, this is a concept from a previous lecture. The idea I want to show you today is that we can do the opposite. So if you look at this equation, you might say, all right, what if I take the matrix logarithm of both sides? Then I'll be left with, on one side, the bracket form of omega, and on the other side, the matrix logarithm of the rotation matrix R. And that's exactly what we're going to do. We're going to use the matrix logarithm of R in order to find the bracket 3 version of omega. Now again, this bracket 3 version, it tells us what omega is, but it writes it as a 3 by 3 matrix. And over here on the bottom of the slide, I'm showing you the definition of the bracket 3 operator. You guys might remember this definition. You might remember, yep, it takes a 3 by 1 vector and it converts it into a 3 by 3 matrix. Here we just want to do the opposite. I want to go from this 3 by 3 matrix and go back to the 3 by 1 vector. So I'm going to isolate the elements of this matrix that correspond to the first, second, and third elements of the vector. So if I look at my third row, second column, that's going to be the first element of the vector I want, and that's exactly what I do right here. I take the third row, second column, and that's going to be the first element of omega. Then up here, my first row, third column, first row, third column, that'll give me the second element of omega. And then the second row, first column, that will give me the third element of omega. And so it's a little bit cumbersome, but basically what I'm doing is I'm taking a rotation matrix, using the logarithm to go back to my bracket 3 version of an angular velocity, and then finally pulling out the angular velocity from that skew symmetric matrix. And so I'm left with x1, x2, x3. That is omega. That's the angular velocity that corresponds to my rotation matrix R. And then the bottom 3 elements of x, well, that's just my position vector. So I just extract my position vector from my transformation matrix, and I'm good to go. So overall, this is my process for going from a transformation matrix T into this vector x, which captures the same information, but just writes it in a different way. Okay, so without further ado, I can now introduce an algorithm for the numerical inverse kinematics of a serial robot arm. And I'm going to go through this algorithm step by step. Now, the first step of this algorithm is I need to figure out where is it that I want to have my robot go? Like, what is my desired transformation matrix? I'm going to call that T subscript D. The subscript D is for desired. So the desired transformation matrix. And again, this is the transformation matrix I ultimately want to have my robot achieve. It's the position and the orientation I would like to go, or maybe figure out what joint values are going to make my robot go here. So my goal is to take this transformation matrix and to find the corresponding joint position theta that has my robot reach that desired transformation matrix. And again, that's the whole idea of inverse kinematics, mapping from transformation matrices back to joint positions. Right? So my goal is to find the joint positions that will get my robot to this desired transformation matrix. And my first step is going to map this transformation matrix, this 4x4 transformation matrix, into the 6x1 x subscript D. And that's the code that we just talked about. All right, the next thing in my algorithm is I have to find a starting point. So I'm going to say, I'm going to put theta 0. That's going to be my robot's current joint position. You could think about that as your first guess at the inverse kinematic solution. So I'm going to say, all right, my first guess for a joint value that will reach this desired transformation matrix, that'll be my current joint position. I'll call that theta. And then I'm going to use my forward kinematics, T of theta, in order to find, okay, if my robot is at this current joint position, where is its end effector? And again, I'm going to map that back into one of these 6x1 vectors, and I'll call that x. So as a recap, x of D, that captures the desired transformation matrix, and x captures my current transformation matrix. Theta is my robot's initial joint position. So this algorithm is going to have a while loop. And at each iteration of this loop, I'm going to try to propose a new inverse kinematic solution, and I'm going to test and see how good that is, and I'll just keep cycling through the loop. The condition for termination is going to be the difference between x of D, my desired transformation matrix, and x, my current transformation matrix. And again, I'm using the word transformation matrix. They're not actually transformation matrices, right? They're these 6x1 vectorized forms, but they capture the same information as a transformation matrix. So while there is an error between these two, we're going to keep going through this loop. And just a little note about the notation here. When I use this bracket here, that means the norm, or it's maybe you could think about it as the length or the distance associated with a vector. So I subtract these two vectors and I see the length of their difference. And that's what I use for this norm operator. You can just use norm in MATLAB. So while the error between these two, this norm, is greater than some value, call that sigma, we're going to go through this loop. And in the first step of the loop, I'm going to try to find what direction does my robot need to go in order to reach this desired transformation matrix. So I'm going to take the subtraction between x of D and x. I'm going to call that V. And again, this is a twist, again, twist in quotes, that moves from moves from my current transformation matrix T towards T of D. And you can treat this as just an error between your desired and your actual. So this is a vector that will move me in the direction that I need to go. Now, I want you to think back to our last lecture. In the last lecture, we found a way to go from this desired motion, V, into the corresponding joint position. And so we're going to apply that concept from our last lecture here. And there's just a couple steps we need to go through. The first step is we need to compute the Jacobian matrix. And you guys know how to compute the Jacobian, so we'll just do that right here. I take in my current value for theta, and I compute my Jacobian. And again, because theta is going to change at each iteration of this loop, I need to make sure that this step is within my while loop. This is a very common mistake that people make, is they compute the Jacobian once and then stick with it throughout the whole process, and then they can't get an answer that converges. So make sure you recompute the Jacobian every time you update this value of theta. So here we go. We recompute the Jacobian, and then I use my Jacobian pseudo-inverse that we introduced in my last lecture video. So I'm going to multiply the Jacobian pseudo-inverse times v. That'll give me a joint velocity that moves in the right direction, and I integrate that to find a new joint position. So I'm mapping from this desired twist in end effector space to a new desired position in joint space. So now I want to say, all right, I've got this new proposed position. Is this position satisfactory? Like, is this going to reach my desired transformation matrix? Let's test it. So now that I've got this new value for theta, I'm going to recompute my forward kinematics. And I'm just abbreviating that as FK for forward kinematics. So I'll get my new transformation matrix T, and I want to basically check and see, is T close to T of D? And the way I do that is by converting T back into this vectorized form X. So I'm going from my 4x4 transformation matrix back to this 6x1 vector X. And then I want to look back and see, all right, is this new value of X close to X of D? The idea is that this algorithm will keep going through this process until I reach this condition, and this condition is satisfied. And that occurs when the error between these two is less than some value epsilon. Right? So once my desired transformation matrix is, once my robot's proposed transformation matrix T is close enough to the desired transformation matrix, that's when I'll stop this loop and I'll say, all right, I now have a joint position theta that can reach this desired transformation matrix. So maybe it's a little bit complex when I say it all like that. Let's see what it looks like in practice. So I want to stick with the same robot we had in our last lecture. Now this is a redundant robot. It's moving in a plane. The XY plane is on the screen and the Z axis is coming out of the screen towards you. The robot is redundant because it has 4 degrees of freedom and it only needs 3 to move in this XYZ planar space. So it's got my base right here with my first revolute joint, my second, third, and fourth revolute joints, and then my end effector right here. So here's the robot I want to test. And what I want to do is I want to find the inverse kinematics. I want to find what joint values for this robot are going to move us to these different desired transformation matrices. All right. So I've got this whole process laid out here, and I want to go step by step through the slide. Let's start off on the left. Now here's my desired transformation matrix. This is the position and the orientation I want my robot to achieve. I want it to move to position 2, 2 in the X, 2 in the Y, 0 in the Z axis, and I want it to be oriented at 45 degrees or pi over 4 radians along this rotated around the Z axis. So here's my plot, this video kind of of my robot. Now the base of the robot is at 0, 0, and this is a plot of the X and Y axes. Again, the Z coming on the board towards you. So here's my base, my first, second, third, and fourth revolute joints, and then here's my end effector. And as the video plays, you'll see your robot starting from some initial position, call that theta naught, and eventually reaches this final position, theta end. Marked here in yellow, that is this desired transformation matrix. Really, all I've marked is the desired position, this 2, 2, and then hopefully you can see the robot has this 45-degree angle that we wanted to have this rotation of pi over 4 around the Z axis. So at the beginning of the video, the robot's at some arbitrary joint position, and by the end of the video, we found a joint value that achieves this desired end effector this desired transformation matrix. All right. So there we go. That's an example of success with our algorithm. We started off with some initial joint value. I gave my robot, okay, I want to have this desired transformation matrix, and I was able to find the joint value that will achieve that transformation matrix. I solved my inverse kinematics problem. Let me show you another example. Same setup. I have the exact same desired transformation matrix I want to achieve. Position 2, 2, and again, oriented at pi over 4 around the Z-axis. But now the difference here is I'm starting in a new joint position. So I've got a different value for theta naught. And you might notice, if you compare these two videos, that in both cases, the robot converges to a solution. It finds, all right, this joint value will achieve this transformation matrix. So it solves my inverse kinematics problem. But it finds a different solution between these two different videos. Here, I've got this joint value, and you can kind of think about this maybe as an elbow up solution. Whereas in the previous slide, if we go back to it, sorry, one second. Here we go. If we go back to this slide, you might notice that the robot has an elbow down solution, and it has a different vector right here. So this goes back to one of the challenges of inverse kinematics. We found two valid solutions, but they're different. And that often occurs because there are many different ways, in most cases, there are many different ways that the robot can reach some sort of different transformation matrix. And so I have many different inverse kinematic solutions. Neither of them is wrong. It's just two different solutions, and they change based on your initial position. So if you use this inverse kinematics algorithm, you'll get different answers based on your choice of theta naught, your robot's initial configuration. Okay, cool. So I want to show you one other video. And in this video, I'm trying to reach the exact same transformation matrix, and I know I can achieve it. The last two videos, we got two different answers that achieve it. But you might notice that the robot is kind of spazzing or jumping as it tries to move to this transformation matrix. And I want you to pause this and just think for a little while, why is my robot having these kind of irregular motions? And as a hint, remember that within our inverse kinematics algorithm, we use the Jacobian pseudo-inverse. So we needed to compute this Jacobian pseudo-inverse. And over here, this is kind of under the hood. This is the equation that we're using to find that pseudo-inverse. All right, so maybe if you thought about this, you recognize that there are a couple things that could be going wrong. And I want to list them in the next slide. So there are a few reasons why the inverse kinematics could fail. Now, the first and probably the most obvious is if your desired transformation matrix is outside of your robot's workspace. That means that there's no physical way for your robot to reach this desired position, and so obviously your inverse kinematics algorithm will not be able to return a valid solution. So that would be one failure case. Another failure case that is a bit more pernicious, and it actually relates to the video I just showed you, is when your inverse kinematic solution moves through a singular position. And so if when you're computing your inverse kinematics, you move through a position theta, in which your robot is at a singularity, this Jacobian pseudo-inverse will explode. Specifically, remember you're taking the inverse of your J transpose. Well, at a singularity, the Jacobian is dropping rank. And so when I take the inverse of this that is now no longer a full rank matrix, it goes towards nan or infinity. So different solvers or different implementations maybe deal with this in slightly different ways, but just know that this is a fundamental issue that deals with the Jacobian itself. And although it's a numerical problem, it's also a physical problem, because what we're basically saying is, I've got my robot, I want it to move its end effector along some twist V, but because I'm in a singular position, my robot can't achieve that, physically, it cannot achieve that twist. And so that's why you see these sort of spazzes in the robot's motion. And it's just something you want to avoid within your numerical inverse kinematics. And then a final way that this could fail is through your choices of alpha and epsilon. And these are two different hyperparameters in the algorithm I just showed you. So alpha is your step size, so how quickly your robot is moving. And in general, you want to have a smaller step size so that you don't miss a good value and perhaps skip over the solution by having too large of an alpha. And then epsilon is how close you want your robot's final transformation matrix to be to the desired transformation matrix. And if you make epsilon too small, you're basically requiring too much precision, and perhaps that precision can't be achieved with your current alpha value. I think this third case is probably something that makes the most sense through some trial and error. So as you practice and you go through the practice set attached, you'll get a better sense of how tuning these two parameters could cause this algorithm to succeed or to fail. Okay, so in this lecture, we talked about the inverse kinematics, and we finally came up with an algorithm that we can use to find the numerical inverse kinematics. We also talked about some failure cases for this algorithm, and I encourage you to go through the practice set. You can see that either in the discussion or the pinned comment in order to see this for yourself and to try out the inverse kinematics. Before we end the lecture, I want to have one final aside. So I'm going to go back to these videos. Now, in this video, I'm showing you the robot moving. And so I think it's pretty natural for you to think, all right, when I do the inverse kinematics algorithm, I'm actually moving my robot arm, like I'm physically moving it through space. That is an easy misconception to make, but it is not correct. The algorithm that I'm showing you, let's go to this slide right here. This numerical inverse kinematics algorithm, I can evaluate this algorithm without moving my robot at all, right? To do this algorithm, all I need to do is just think about my Jacobians and think about my forward kinematics and use some of the kinematic relationships that we've already built in order to solve for a value of theta. No actual motion of my robot is necessary. And so when robots implement this algorithm, they're not actually moving. They're just using this algorithm with the input value of theta, and then ultimately they're outputting some final value of theta saying, all right, if you wanted to achieve this desired transformation matrix, here is the value of theta that will reach that transformation matrix. So the result of this algorithm is not moving the robot, it's just telling you a value of theta, a joint position that will achieve your desired transformation matrix, which again, that's really what we wanted from our inverse kinematics. So a very common misconception. All right, with that said, let's go to in the next lecture. And so once you've completed your practice set and kind of thought about this inverse kinematics, we're going to start changing gears and going from kinematics into dynamics. And that's when we can really start thinking about how does our robot move and how does the physical embodiment of the robot change different ways that it can move in our space. So I look forward to seeing you there.